So in the last video, when we were discussing the integral test, we saw this concept here. Let me show it again. So this kind of idea right here, where we saw that when this infinite series, if we know it is less than some finite number, right? We know that it's less than something else which did converge. In this case, it was an integral. Then that told us that this also converges. Okay. So when we say that something converges, we mean that it's finite, right? That we mean that the answer to the what this sum is a finite number. So if it's less than some other finite number, then of course it's going to be itself a finite number. We saw the opposite right here, right? Where the sum is greater than infinity, so that must mean that it is infinity, right? Because there is nothing that's greater than infinity. In this case, if you're thinking about things where it's less than a finite number, you could technically have it go to negative infinity, but that's ruled out by the fact that all of the terms were positive, right? So there was no chance of it going to negative infinity. But in general, that is something we need to consider, right? So if the terms are positive and we know that it's bounded by some finite number, then we would know that it converges. So we want to take this idea further and expand it into its own test called the comparison test. And in this case, we were comparing it to an integral. But what we want to do is we want to compare a series to a different series. So we'll start with an example here. Okay, let's consider the series of 1 over n squared plus 1. Okay. Now, this one, there might be other ways you can do this. Like you might be able to do this with an integral test. But the easiest way to do this is to realize that, okay, n squared plus 1, keeping in mind that n is a positive number, but even if it's not, n squared definitely is. This is always greater than n squared, right? Because we're, this is on the left, this is the same thing, we're just adding 1 to it. So of course it's going to be greater. So if we were to put them in the denominator, the opposite inequality would hold, right? The left one now has a larger denominator, meaning that overall it's going to be smaller, right? They have the same numerator. This one has a larger denominator, which is going to make it smaller, right? Just like 1/4 is less than 1/3. So when we consider the infinite series of n equals 1 to infinity of 1 over n squared plus 1, this is definitely going to be smaller than the infinite series from n equals 1 to infinity of 1 over n squared. Because every term in this series is smaller than every term in this series. Okay. This one over here, we know is convergent, right? We know it's less than infinity. We said that we did show, I wrote down specifically that it's equal to pi squared over 6. And that's not an easy number to come up with. I did link a video kind of relating to that, but I mean, it's just kind of like an extra thing. Not really something we want to get into. But we're not really concerned about what number it actually is. The important part is just that it's less than infinity. Since this one is less than infinity, and this one is less than the 1 over n squared, then we know that the 1 over n squared plus 1 must also be less than infinity, meaning it converges. So this implies that n equals 1 to infinity of 1 over n squared plus 1 is also less than infinity, meaning that it does converge. Okay. Now, this doesn't give us, really a way to find out what it converges to. of course. But I'll reiterate, oftentimes we're really just concerned about if it converges at all. So let me write down the actual test here, and then we'll do some more examples. So the comparison test, we do need to be very careful about the direction of the inequality. Okay. So the first part of this here is suppose that there exists an integer n such that 0 is less than or equal to a sub n is less than or equal to b sub n. So this is implying that the terms need to be positive, like I mentioned. Okay, so for all n is greater than or equal to n. So the terms need to be positive. That's what the a sub n greater than or equal to 0 implies. But then a sub n is also less than or equal to b sub n for all n past a certain point. So again, just like we've seen before, it doesn't necessarily, this inequality doesn't need to hold for every single n, but it has to from some point onwards, whether that's the first number or the millionth number, somewhere between n to infinity, it needs to hold. Then if the sum of b sub n converges, then the sum of a sub n converges. Okay, so some positive sequence a sub n is bounded by some sequence b sub n. So if that sequence converges, then we know that this one must also converge. So again, it's because every single term in this sequence a sub n is less than every single term in this sequence. So the sum overall is going to be less than or equal to the sum overall of this one. So if this one is finite, this one must also be finite. So then the other side of that is the divergent part of this. Okay, so suppose that there exists an integer n such that a sub n is greater than or equal to b sub n is greater than or equal to 0 for all n greater than or equal to n. So still need to be positive, but now the a sub n's are greater than the b sub n, so that one's flipped. If the smaller sequence, the b sub n's, diverges, the smaller sum, I should say, not sequence, then the larger sequence, in this case a sub n, also diverges. Okay. So we didn't look at an example of this one yet. Well, we did kind of an integral test, but let's just look at, if we take n minus 1, we know this is less than n. So this implies that 1 over n minus 1 is greater than 1 over n. Okay. Now, we know, I'm going to start this at 2, just so that this one isn't undefined at any point. But that's not going to change anything. But we know that this sequence over here diverges, right? We've already seen, meaning that it's going to infinity. So if this one is larger than something that's going to infinity, then it must also go to infinity. All right, so this one also diverges. Okay, so that's how we can use the comparison test. So this kind of opens up a lot of different series that are close to series that we're familiar with, or it can cut out a lot of the work because we can just look at an inequality and look at a simpler series. right? Now we do need to be a little bit careful of this one. Okay. So for example, n is less than n squared, right? Which implies that 1 over n is greater than 1 over n squared. So we know that this is true, right? That this sums, the inequality will hold. Now we know that this one diverges, but that doesn't tell us anything about this one. So this is just telling us that it's less than a divergent series, right? So it kind of looks like you're saying that it's less than infinity, but that's not really what you're saying. You're just saying that it is less than some divergent series, but rather the sums themselves, the individual terms are less, but they could both be going to infinity, right? So we don't know if this inequality really holds. So maybe I shouldn't even write that at all. Okay. So this comparison test, it only works in the specific instances that we have written here. Okay. So in this case where we have a divergent sum and this one is less than it, we don't necessarily know that it converges or diverges. It might still diverge. It might, not. So if we're looking at something like 1 over n plus 1, okay, this is going to be less than 1 over n. And when we try to compare them here, we get the same idea. Okay. And this one, we know diverges. So I keep writing this, but we really shouldn't write this unless we actually can do the comparison test. This one diverges, so that doesn't tell us anything about this one because it's smaller, right? It would only work if this inequality was a greater than sign right here. So when something is smaller than a divergent series, we don't know anything about it. So we got to be pretty careful when we're making these comparisons, not to run into this problem. So even though 1 over n plus 1 looks like a very similar series to 1 over n, using the comparison test alone, we can't really say anything about it. In this one in particular, you could just do with the integral test. Like you could just use the series of 1 over x plus 1, or the function 1 over x plus 1. Okay. So let's do some more examples here. So let's say we have something like, we get the sum of 1 over n cubed plus 3n plus 1. Okay. So we want to look for something we can make a comparison with here. Well, this one is going to be less than 1 over n cubed. Okay. So this can be a little bit tricky when you're working with the denominators, but this is because n cubed is less than n cubed plus 3n plus 1, right? Keeping in mind, again, that n's always positive here. So when you put them in the denominators, that will be reversed, right? So you could just do it like this. So you want to be very careful making these comparisons, but this is indeed less than 1 over n cubed. And this one we know is finite by because it's a p-series, right? Which is an extension of the integral test. Okay. So this one then we know converges. Okay, so again, we're not getting anything about what it converges to, just simply that it does converge. Let's look at n equals 2 to infinity of 1 over the natural log of n. Okay, when we start the index at a different number, it's not going to affect whether it converges or diverges, right? A convergent series should converge whether you started at 1 or 10 or 20, and same with a divergent series. What it would affect is what it converges to, right? That's going to be a little bit different if you take some of the terms away, but we're not really looking at what these converge to anyway. So if we're actually calculating what it converges to, like if we're using the partial sums, or if it's a geometric series, then what that index is will affect it. But in these cases where we're just looking to see if they converge or not, it's not affecting anything. So the reason we're starting this one at 2, of course, is because natural log of 1 would be 0, and that would make the denominator 0. So here we want to look for a comparison. There's probably a few different things you could do here, but we could note that n is greater than the natural log of n, specifically when n is greater than or equal to 2, which is where we're starting. And sometimes, you might only be able to find a relationship starting at a specific number, and that's fine because that works in the comparison test, right? So even if the relationship doesn't work until you get to 5 or something, that's fine. This might not be immediately obvious though, right? So I think a better way to see this would be, okay, well, e to the n is greater than n is what this would imply. And I think that one is a little bit easier to see that it's true, right? Because clearly e squared is greater than 2, e cubed is greater than 3, e to the 4th is greater than 4. Just keeping in mind that this is a little over 2, right? I think that way it's a little bit easier to see. Maybe it's already easy to see without doing that, but regardless, this is the comparison we want to make, and we're putting this in the denominator. So we're saying that 1 over the natural log of n is greater than 1 over n. Okay. So n equals 2 to infinity of 1 over the natural log of n is greater than n equals 2 to infinity of 1 over n. And this one diverges. So that's going to imply that this one diverges as well by the comparison test. Okay. And again, the index being different here isn't going to change anything. It's still going to diverge, right? That's like saying infinity minus 1 is still infinity, right? Or any finite number. So this can be a little bit tricky to see, what exactly do we want to make the comparison to? It's not necessarily always an easy task. So this is just something that kind of just comes with practice. You really just have to play around with it. You want to usually try to compare it to something easy. Like one of the P series is probably the most common. Maybe a geometric series if it's set up that way. Okay. But in general, I think that it mostly just comes with practice, where you start to see the most common series that you'll making comparisons to. I want to do a few more here just to kind of, get some of that practice. So like this one right here, we already saw that 1 over a similar series was less than n cubed. So we could say that this is less than n over n cubed, right? Because we already saw that 1 over this is less than 1 over n cubed. So the n being on top, we'll just keep it on top. And now we can simplify that a little bit to 1 over n squared. And this converges. Okay, so then we're good. So just things like that. Again, I would say the most common is probably a P series, but there's other ones that will come up, of course. Let's see, what about one with a factorial here? Like, what about simply n equals 1 to infinity of 1 over n factorial? Okay. This one, I think immediately you should recognize this is probably going to converge, but we need to actually show it. We think it would probably converge because the terms go to zero really fast, right? Like that's the difference between 1 over n and 1 over n squared converging, is that the 1 over n squared terms go to zero faster. Here, they're going extremely fast, right? So again, keeping in mind the p-series, maybe we can say, well, n factorial is definitely greater than n squared after a certain point at least, right? At 1, this is not true. At 2, this is not true. At 3, this is not true. At 4, now it's true. Okay, so when n is greater than or equal to 4, that's when this starts being true. So it doesn't need to be true right away. It just needs to be true from some point onwards, right? So after 4, this left side is going to take off, and now it's always going to be greater. So this is the opposite then will hold true if we put those in the denominator. So this is less than n equals 1 to infinity of 1 over n squared. So that's one that we know converges by the p-series. So we say that this converges. Okay. So sometimes trig will come up in here. I won't say too much about that, but just keep in mind that if you have sine of anything, it doesn't matter what's in there. This is always less than 1, and same with cosine, right? Cosine and sine are bounded by 1, so it doesn't really matter what's in here. That's just one that I'm looking at right now. But if this is n squared, natural log of n, whatever, this is always less than 1, so that can always be helpful. Like the one in particular that I'm looking at here is sine of 1 over n squared. So since sine of anything is less than 1, we know that this is less than 1 over n squared, which is convergent. So we say this converges, so we can do things like that. So yeah, so often, again, we just really want to be familiar with those p-series because that's usually what we're going to compare to.